Hey folks, welcome to this episode on reaction mechanism. So when we've been looking at reactions so far, we're making the assumption that the reaction happens in one step. A plus B gives us C and D. But in actuality, many reactions actually take place in a number of steps. And we call these series of steps the reaction mechanism. So a reaction mechanism is really just a series of steps of what we call things called elementary steps. And these elementary steps are just a single step in a series of very simple reactions that make up the overall chemical reaction at the atomic level. So when we say A plus B gives us C plus D, for example, this may not happen in one step. A might not just be able to combine with B to create C. A might combine with something else to produce something what we call an intermediate, and then that intermediate reacts with B to produce C and D. So this can happen in one step, but more likely than so, it happens in a number of steps. When we look at this example over here, we have dinitrogen monoxide, and that decomposes into nitrogen and oxygen gas. Instead of happening in one step, it actually happens in two elementary steps. First, we have this step over here. We'll create our N2 and O, which is interesting because we know that oxygen has to be a diatomic molecule in regular conditions. And we see O2 here, but we only produce an O over here. Now, what's going on here? Well, this is our intermediate. That's what we're saying over here. As you can see in the next step over here, dinitrogen monoxide reacts with this individual oxygen atom to then produce N2 and O2. So now we combine the N2 that was produced here, and we get our 2N2, and we get our one molecule of oxygen, and we get our overall reaction as we saw here. So this is very similar to what we were looking at Hess's law in when we were studying our enthalpy, where we had some intermediate steps, and then we were able to cross them out and get our target equation just here. Now, how do we know what kind of mechanism is being used in these series of reactions? Well, we can turn to a place of chemistry called femtochemistry. And femtochemistry uses light and laser pulses to actually monitor the chemical reactions. Now, let's say we had a chemical reaction. If we go back to our A plus B gives us something. Now, in here, we might actually form an activated complex before we can get into our final products. How do we know what that activated complex is? How do we know what the activation energy is? We use femtochemistry. Now, let's say we have A and B, and we want to see what the activated complex is here. Well, femtochemists will actually do something using pulses, or pulses of light. The first pulse will go ahead and provide the amount of energy required to overcome the activation energy. Now, this allows this reaction to happen and produce our activated complex in a transition state. The second pulse, so the first one will be here to provide our activation energy. The second one will be looking to see what wavelengths are going to be absorbed and by how much. This will give us information about what the structure is of our activated complex and the changes in the bonds that are occurring. So, remember when we were looking at activated complex, we used dotted lines to show the formation and breaking of bonds that are happening simultaneously. We can look using femtochemistry of what bonds are being broken, which bonds are being formed, which will then give us an idea of the overall structure of our activated complex. So it's a really interesting process in these two pulse systems, where we can study an activated complex that only exists for about 10 femtoseconds. Now look at that, 1 femtosecond is equal to 10 times negative 15 seconds. So we're studying activated complexes that really are transient. It allows us to really look at the progress of our reaction and also gives us an idea of what the actual structure of these activated complexes are. So our rate determining step is one of our more important steps when we're looking at kinetics of a reaction. The rate determining step, or sometimes it's called the rate limiting step, it's the slowest elementary step in this multi-step or series of steps of this reaction. And it is the one that limits the overall rate for the entire reaction. Now let's take a look at this example here. Here we have 4 vehicles in a line. We have a minivan that could probably go about 120 kilometers, 130 kilometers per hour. Here we have this car, it might be able to go, somewhere between 140, and we have this other sports car over here that might be able to push 200 kilometers an hour. and they're on this one-way street. We don't know what the speed limit is, but let's say the speed limit is infinite. This tractor trailer is actually holding all of them up. Regardless of how fast all of these cars can go, in this case, they can only go the maximum speed of this tractor trailer. Let's say that's going 30 kilometers an hour. So as long as they're behind here, their speed or their rate is limited by this slowest moving tractor, and this tractor would be the rate determining or rate limiting vehicle for this traffic. Now, once this tractor moves out of the way, these cars can just pull ahead and go as fast as they can in their theoretically really, really high speed. But as long as they're behind here, they're limited. So the same thing happens for a reaction. We might have a number of steps that they take, step number 1, step number 2, step number 3, and altogether you're going to get your target equation. And if we have one of these that are going to be our rate limiting, so this, let's say our first one, limiting step, if this first step is our rate limiting one, then the entire reaction is going to be based off of this one, because whenever we form the products from this rate limiting, they're automatically going to be used here, and then automatically going to be used here to use our final products. So these steps 2 and 3 can be very, very quick, but they're all depending on the formation of this product. Once this product is made, it's going to be used to form a new product, and then take that product and form a new one. We're all waiting on this product over here. So the rate limiting step is the one that really controls the rate of the overall reaction. And it doesn't really matter where this rate limiting step is located. In this series of beaker pores through funnels, in this case you can see that we have 2 big funnels over here and one small one. The small one's here, the small one is here. Regardless of where it is in the step, the first step or the second step or the third step in a 3-step reaction, it's going to limit the rate of the entire reaction. And that's why we say that this rate determining step or the rate limiting step is the one that controls the rate of the entire reaction. Regardless of where it is, it's going to control that entire rate. So once this funnel is slowly pouring the water, you can see that this next step is using the water almost immediately. There's no backup over here. It's going straight into the next one, and then coming up to our final product. This one, you can see there's a little bit of a backup over here because this step can only progress as quickly as this step. But again, this is still the rate limiting step, because once the product's going to be made over here, boom, it's going to be converted to the end. And finally, the same thing, we have a little bit of backup over here because our rate limiting step is at the end. But once again, once this is getting made, well, we're done and we finish our reaction. These rate limiting steps, and when we're going back in our order of reactions, they give us an idea of the mechanism of which the reaction occurs. So let's take a look at this reaction over here. We have HBr reacting with O2. We can see that there's a proposed mechanism over here, and these are the 3 steps that this is going to be occurring in. HBr reacts with O2 initially to create this intermediate, HOOBr. That intermediate is then used up by reacting with another mole of HBr, so we've used 1, we've used 2, to create 2 moles of HOBr, and then both of these moles are going to be reacting with 2 moles of HBr, so now we have 4 in total, to produce H2O and Br2. And in this case, what we should have is we should also have 2 moles here and 2 moles here, hence the bracket outside there. So we've created 2 moles of H2O, 2 moles of Br2. We used 4 moles of HBr, 2 over here, and 1 mole of O2, which gives us our target equation. Now, when we look at the kinetics behind this, we see this kind of distribution. Now, this distribution allows us to get an idea of this mechanism. And so this mechanism was actually created through the analysis of this curve over here. We can see that for every hump in this curve, that equals a step in the mechanism. So for each curve, we have an elementary step. So we should have 3 elementary steps. 1 over here, 2 over here, and 3 over here. And those line up to 1, 2, and 3. So the humps tell us, or the peaks tell us, how many elementary steps we're going to have in our reaction mechanism. The other thing that this graph tells us is the amount of activation energy that has to be overcome for each of those elementary steps. The first one you can see has the highest amount of activation energy. This one has this much of activation energy, and this one over here. the more amount of activation it has to overcome, the slower the reaction. It has to be able to have those particles hit in the correct orientation with enough kinetic energy to overcome that activation energy. The higher the activation energy, the lower probability that that will actually happen. And so in this case, because we have a higher activation energy, this one over here is going to be our slowest step. And because it's the slowest step, we call it our rate determining step, and therefore it is also representative of the entire rate of the reaction. So the rate of the rate limiting step would be, and remember that R is equal to some constant, the constant of this reaction, multiplied by our reactants to the power of whatever. Those powers of whatever are what we call our orders of reaction. So here are two reactants. So R is going to be equal to some constant multiplied by the initial concentrations of our reactants, HBr gas and O2 gas, raised to some exponent. And those exponents we would have to know experimentally. Now, because this is the rate limiting step determines the rate of the entire reaction, and therefore this is also the rate of the reaction. Once this HOOBr is produced, it's going to be quickly used to turn into 2HOBr, and once these are being used, quickly it's going to be converted into 2 moles of H2O and 2 moles of Br2. So let's take a look at a reaction mechanism. Here's our first example. We have this compound over here, CH or CH33, CBr, and it's being reacted with OH minus. You can see very quickly based on this reaction that there is a displacement between the OH and the Br. The Br is being displaced by the OH and being left by its lonesome. Now, what this study shows in analysis of this reaction is that this is first order for 2-bromo-2-methylpropane, and it's going to be 0 order for the hydroxide ion. Now, what that means, remember that in this case that the concentration for OH minus would be 0 order, and for this one, this would be bracketed, and if it's first order, it would have 1. Now what that means, remember what the orders mean, 0 means that no matter what we do to our concentration, it has no effect on the rate whatsoever. And a first order means that if we double this concentration, we double the rate. If we triple this, we triple the rate. If we quadruple this, we quadruple the rate. So there's a linear relationship between this and this. So in this case, because this happens, because OH has no effect on the rate whatsoever, it suggested that this is not going to be a straight one-way reaction. In fact, it's going to be a complex multi-step reaction. So it might take 2 steps, 3 steps, 4 steps, but it certainly will not take 1 step like we might assume it does. Now, when we look at this, as we learn more and more about chemistry, this is what we call an SN1 reaction. Now, an SN1 reaction, if we just kind of write it out here, SN1, this stands for nucleophilic substitution in the first order. Now, this is also called unimolecular. It's a unimolecular reaction. So what happens is that, we'll see in the next slide, that the bromine over here actually has to break away from its structure over here. Now, it produces something called a carbocation. This step of bromine leaving this structure over here is incredibly slow, and therefore is the rate determining step. That's why it's a first order reaction in terms of rate. The whole rate of the reaction depends on this bromine actually leaving this complex. It doesn't matter, no matter how much concentration you have over here, it won't affect this reaction. It has to basically happen by itself. But once it does, then this structure will quickly react with this to produce this product over here, and again bromine will be by itself. So once the bromine actually ionizes from the structure, creating this carbocation, it quickly reacts with the OH and produces our product over here. So this is what it really looks like. In this case, again, this step is very slow because bromine basically has to break off from this structure by itself. Now, once it does, it takes the electrons with it. You can see that here we have 1, 2, 3 pairs of lone pairs of electrons. Here we have 4. And remember that this bond is made up of two shared paired electrons. So these electrons basically leave with the bromine, make it a negative, and this forms a positive. The name of something that has a carbon with a positive is called a carbocation. Cation. There we go. Carbocation. So this carbon has a positive step. Now, this step, again, is very, very slow. The more stable this carbocation is, the faster it will form and the faster the reaction will be. So in this case, this is not very stable, and that's why this reaction is going to be very, very slow. Now, once this is produced, you can see that this right here, this carbocation, is an intermediate. It's an intermediate because it's not found in our overall reaction, and it's also used up in the next elementary step. So you can see that here it's being used up, and here we have OH minus. You recognize it as hydroxyl group. We also call this a nucleophile. Nucleophile. So a nucleophile is a species that is basically, when we talk about nucleophile, philic means to love. Nucleo is nucleus, so it's a nucleus-loving species, and it's the tendency for an electron-rich. We can see that this has a lot of electrons to be attracted to the positive nucleus of an electron-poor species. In this case, what we call that a carbocation. This would be called an electrophile. So in this case, the OH minus will be attracted to this positive area. This is a quick reaction because this is basically waiting. It's waiting, it's waiting, it's waiting for this to be produced. Once this is produced, boom, it reacts and it produces this species over here. And we get to that. So you can see that it's not a one-step reaction. It actually takes 2 steps. And the reason that this is going to be 0 order is because no matter what we do, we can pump OH into here, but it won't affect the speed at which this ionizes and forms this carbocation. This is very, very slow. Once it does it, OH will react quickly and create our final product. Now here we have a second reaction mechanism, and we have something very similar. We have CH3CH2Br. This is bromoethane, and reacts with, again, this nucleophile OH. And you can see that this reaction, again, is a displacement reaction where OH takes the place of Br. However, what's interesting is that in this case, both the OH and the bromoethane are first order in terms of the rate of the reaction. So this allows us to figure out that it's probably not as complex as the one that we saw before. And in fact, it isn't. When we look at this, both of these have an effect on the overall rate of the reaction, which means that this is probably not happening. Last time we were looking, we were saying that this autoionization, we were looking at bromine autoionizes into this bromine ion and therefore creates a carbocation. Now that was a very, very slow reaction, which means that this would be the rate determining step, and that would also mean that OH would have no role. If this was the case, OH would be actually 0 order. However, we know that in this equation over here, both the bromoethane and the OH are first order, so this cannot be right. There has to be something else going on. And this is what we see over here. Now this is what we call an SN2 reaction. SN2, and as you guessed it, it's nucleophilic substitution, second order, and we call this bimolecular. So this is bimolecular because it depends on 2 molecules. Here we have our first one, here we have our second one. So this nucleophile, OH minus, actually does a little bit of a sneak attack. It kind of provides assistance for this reaction to happen in a quick, smooth step. What it does is it actually attacks the backside of this carbon that's attached to the bromine. Now, we know that this is going to be a polar bond, and so this is slightly positive, which is why the OH is attracted to it. Now, there's a few different other items that influence how easily this is done. We call it hindrance or steric hindrance if these are really, really big, but in this case, we only have hydrogens. They're small little atoms, so this can fit in nicely. So this attacks the backside, and what you can see is that we have this little step over here, where we have our dashed lines. Now what this is showing is that simultaneously this is bonding on and this is being displaced. And so we have the simultaneous reaction, and finally the bromine will be displaced, so we'll have bromine by itself, we have its lone pairs over here, and we'll have this final product over here. So you can see that this actually happens in one step. This OH simultaneously latches on while the bromine is being displaced, and this allows for this to be dependent on both this and this molecule over here. If we increase the concentration of this or we increase the concentration of this, this will allow this reaction to happen more quickly because it depends on both of these. So that's it very much. That's it for now, folks. Thanks very much for watching. We'll see you next time.